The topic for today's presentation is landfill gas technology and potential. In this presentation, we will cover landfill gas, landfill formation, landfill gas technology, landfill gas application technology, estimation of LFG potential. So, starting with what is landfill? When waste is disposed at a particular site and it is buried in a systematic way, it is known as landfill. So, now moving on to landfill gas. It is a natural byproduct of decomposition of the organic material in the landfill. It is composed of 50% methane, 50% carbon dioxide, and small amount of non-methane organic compounds. It is also classified as medium heating value gas and which is 18.3 megajoule per cubic meter. Landfill formation. Below are the steps which we will be discussing one by one. Site layout, site preparation, materials requirement and balance, phasing, cells, bunding, cover material, and landscaping. Site layout. It shows a detailed location of the whole site. It should clearly tell about the location of the area to be landfilled. A topographical map should be prepared, and the typical scales used are 1 ratio 500 or 1 ratio 2500 for the larger sites. So, this is a picture depicting the site layout. Site preparation. For different activities, the landfill site is prepared, such as a lining system for cell, gas management facilities, ground and surface water systems, and all other site infrastructures. Material requirement and balance. Material such as soil, it is required at all the stages such as construction, operation and restoration. So it is important that the designer should estimate the quantities of the material required. Requirement of materials is for basal mineral liner, cap barrier layer, gas collection and venting system, roads and embankments. So, to obtain the balance, the deficient material needs to be imported. Phasing. Landfill should be developed in a series of phases as it helps in progressive use of landfill area for good working of construction, filling, and restoration simultaneously. To avoid frequent and disruptive preparatory works, it is recommended that the design of lifespan of a phase should be minimum 12 months. Factors considered in determining phasing are waste intake that determines the size, lifespan of a phase, and sequence of operation. Moving on to cells, these are subdivisions of phases and helps in easy going of the work. Bunding. It is used for perimeter screening, whose height varies from 2 meter or more. Boundary bunds, which is division between the cells, and temporary screening, whose height is 2 meter and slope is 1 is to 2 is to 5. Next is cover material. There are two types of cover material, daily cover and intermediate cover. Daily cover is the material spread over deposited waste that is about 150 mm if soil cover is used and it is permeable. Intermediate cover, it is placement of the material for a period of time prior to restoration that is 300 mm. And the last step is landscaping. Basically, it is the end use of the site and presenting a clean and well managed appearance to the public. Now, moving on to landfill gas production. These are the three processes by which landfill gas is formed: bacterial decomposition, volatilization, chemical reaction. In bacterial decomposition, the organic waste is broken down by bacteria, which is present in the waste and in the soil that is used to cover the landfill. Volatilization. Landfill gases can be created when certain waste, particularly organic compounds, change from liquid to vapors. That is known as volatilization. And the last one is chemical reactions. Landfill gas can be created by reactions of certain chemicals present in the waste. Moving on to landfill gas technology. Landfill gas is collected by various extraction systems like gas vents from the landfill bed, vertical wells, and horizontal pipes, header pipes discharging gas to the collection point, and collection station that is demoisturizers, blowers, measuring or performance monitoring equipments. There are some of the elements of installation for gas extraction. First one is vertical gas extraction system wells. Extraction wells built on a layer of soil serves as an additional landfill lining. More stress is reduced on the geomembrane and due to which the landfill lining is not damaged. Solid waste is deposited and compacted around the wells and a filter is mounted at the lower part of the well. Here is the picture showing the vertical gas extraction system. The second one is horizontal gas extraction system, where horizontal pipes are used. In this, the total landfill surface area is divided into cells, which is each cell is of 1 hectare, and in each sector, collection pipes are installed that are 200 within waste bed. The pipes are arranged at a sufficient slope, and the gas is transported to the collection stations through the pipes. Here is the picture showing the horizontal piping system. And the third one is vertical horizontal collection system. It is used at the landfill where the solid waste is of thick layer. The horizontal pipes are connected with the vertical wells and it is economically advantageous. Now moving on to landfill gas application technologies. There are several ways to effectively utilize landfill gas for energy. Firstly, it is directly used in process heat generation, infrared heaters, leachate evaporation, and it is a very cost effective method. Second is in electricity generation. It is produced by burning landfill gas in reciprocating engines, turbines, microturbines, or Stirling engines. It is very beneficial, and about 90% of the landfill gas projects are in Poland. And the third one is biomethane production, which is done by pressure swing adsorption and membrane separation. Now we will discuss about the estimation of LFG potential. Basically, there are three methods available for LFG emission estimation. First is simple rough approximation method, second is model estimation, and third one is field measurements. And one by one we will be discussing on these three. Starting with simple approximation method, in this only amount of waste is taken to estimate the gas. The ratio of waste quantity to gas flow is the procedure for estimating the approximating gas production. It reflects only the average landfill that has a gas control system or energy project, and it may not reflect the waste and climate. Therefore, this method is primarily used as a screening tool for initial project planning. According to a report given by US EPA, the LFG generation rate changed from 3 to 12 cubic meter of gas per ton of the waste per year. Model estimation. It is the practice of forecasting gas generation and recovery based on past or future waste quantities. These models are used for evaluation of feasibility of LFG energy projects, determine gas collection and control design requirements, performance due to diligence evaluations of potential or actual project performance. Now we will know about the description of LFG models. Basically, all the models have two parts for the estimation of the LFG. First is the description of the total methane potential, that is L naught, which is the total amount of LFG formed during the lifetime of the landfill. And the second is the function FT that describes how this potential is released over time. So, which fraction of the total methane potential is released in the first, second, third year, and so on. Hence, the total LFG generation GT in year T can be described as GT is equal to W into L naught into FT. Now we will be discussing about the three models in which LFG generation is estimated and the results are compared. The first one is LandGEM, second is Tabasaran and Rittenberg, and third one is multi-phase. In this, environmental factors, characteristics, and compositions of the waste were evaluated. Starting with the first model, LandGEM. This model uses first order decay. First order decay consists of two parameters, that is L naught and K. And here's the mathematical expression given, in which Qt is estimated methane generation flow rate, L naught is potential methane generation capacity, Mi is mass of solid waste disposed in the ith year, K is methane generation rate, Ti is the age of the section of the waste mass disposed in the year ith. Second model, Tabasaran and Rittenberg. The cumulative amount of gas produced during a certain time is determined by a mathematical model, where GT is the total LFG production in the year, Corg is the total organic carbon, K is the degradation rate constant, T is the temperature, small t is the landfill operation time, Mt is the amount of waste in the T year. The third model is multi-phase model, in which the LFG is estimated on the basis of biologically degradable organic carbon ratio in the waste and the cumulative amount of waste. This is the mathematical expression given, where alpha T is the total LFG production in the year T, alpha T is the dissimilation factor, A is the amount of waste, C naught is the organic carbon content, KT is the degradation rate constant for the waste fraction, and T is the time. The content of waste is divided into three fractions based on the biodegradation rate of the compound, such as fast, moderate, and slow. The multi-phase model describes that kitchen waste degrades much faster than wood or paper. So here is the graph showing the results of LFG generation from LandGEM. To define the differences, we have taken the three decay rates which are given below, that are 0.35, minus 0.1, and minus 0.05. So the landfill operation, as we can see in the first year, the generation is approximately 44 million cubic meter, and then it keeps on increasing until the last year of the operation. In the last year of the operation, approximately 138 million cubic meter of LFG is generated for high decay rate, and after the closure of the landfill, the amount of gas is reducing for all the decay rates. This graph shows the LFG generation by Tabasaran and Rittenberg model. In this, we can see that the maximum LFG generation reaches approximately 145 million cubic meter in the end of the fourth year. After that, approximately after 2 years, there is a sudden drop, and after that, it is constantly decreasing. This graph is plotted using multi-phase model. In this, we can see that the graph is climbing steadily, and the maximum LFG generation obtained approximately was 32 million cubic meter at the fourth year. After that, it is flattened out at the next periods. But one thing we can surely see here is that if we compare this model to another model, we can see that it has been gone for longer time. As compared to the Tabasaran and Rittenberg model, this LFG generation is spread out over a longer period of time. This is the graph showing the comparison of all the three models which we have discussed before. Considering the fourth year is final year of waste placement, all models show peak methane gas generation in the end of the waste placement. The peak of the graph demonstrates final waste placement at the area for all models. So here I've taken an example of the landfill sites located in Mumbai. The three sites they're given here: Dinar, Muland, and Gurai. The landfill size of Dinar is 132.1 hectare, Muland is 25 hectare, and Gurai is 19.6 hectare. And the waste in place, the maximum is in Dinar, as the size is large, it's 7.88 million ton. And year filling began in Dinar is 1927, 1968 in Milan, then 1972 in Gurai. The closure year is Dinar is partially closed, Milan is not yet planned, but Gurai is closed since 2008. And the annual waste acceptance is 1.5 million ton in Dinar. In Milan, that's 1 million ton, and Gurai is zero point 0.4 million ton. So this is the graph depicting the estimated LFG quantities of Gurai, Dinar, and Milan. As we can see, there is a huge difference between Gurai and Dinar. Dinar and Milan are on the same line. We can see here that the amount of gas produced by Gurai was about 85,000 MCF, and by Dinar was about 2,30,000 MCF. And with the time, they have been decreasing.